In this lecture, we will be discussing about evaporation process, principle behind the evaporation, application, types of evaporators, then different types of feed system in the evaporators, then design of evaporators with the stream economy and efficiency of evaporator. In this slide, you can see that the left side we are having a high capacity forced circulation evaporator, whereas in the top you can see the two-stage evaporator with the forced recirculation. That is a schematic representation. Evaporation, literally a unit operation which can be defined as vaporization of volatile solvent by ebullition to increase the concentration of essentially non-volatile components of a solution or even suspension. Vaporization by boiling is emphasized in order to differentiate between evaporation and dehydration. The non-volatile nature of the components over than the solvent leads to the difference between evaporation and distillation. In the case of foods, the volatile solvent is almost always water. Evaporation differs from dehydration since the final product of the evaporation process remains in liquid state. It also differs from the distillation since the vapors produced in the evaporator are not further divided into fractions. This is an important unit operation commonly employed to remove the water from dilute liquid foods in order to obtain concentrated liquid products. It is a step used for removal of solvent from the liquor, that is solution, by application of heat. In this respect, it is different from other concentration operations like membrane separation processes in which the phase change of solvent does not take place. Now we will see the main objective of evaporation. Mass and volume reduction. Because of the evaporation, it leads to mass and volume reduction, which will be resulting in the reduced cost of three things: packaging, transportation, and storage. Preservation can be done by virtue of the reduced water activity. You can use the evaporation for the preparation of subsequent treatments such as crystallization in the case of sugar, citric acid, and so on, precipitation in pectin and other gums, coagulation of cheese, yogurt like products, forming of candy, dehydration with respect to milk, whey, protein, coffee solubles, etc. Building a desired consistency in products like jams, jellies, tomato concentrates, ketchup, and so on. However, it should be noted that the rate of chemical deterioration increases with the concentration. Actually, when you are doing the evaporation, mass and volume can be reduced because more and more solvent will be evaporated. That is why it will be giving you more concentration. Also, because of the reduced water activity or reduce the presence of water, we can use this for the preservation. That is what we told. But the rate of chemical deterioration increases with the concentration. If more concentration means chemical deterioration will be more. So thus the concentrated juices, although more resistant than single strength form to microbial spoilage, tend to undergo browning more readily. Then a typical evaporation process in the manufacture of tomato paste usually around 35 to 37% of total solids. That is, this is regarding the application of evaporation. Of course, in the forthcoming slides, we will be looking into this information. Now, the rate of evaporation, that is the speed of evaporation, is governed by many factors. The factors include rate at which the heat can be transferred to the liquid, Quantity of heat required to evaporate each kilogram of water, maximum allowable temperature of the liquid, pressure at which the evaporation taking place, of course the changes that may occur in the foodstuff during the course of evaporation process. Important practical consideration in evaporations are maximum allowable temperature, which may be substantially below 100 degrees Celsius. Promotion of circulation of the liquid across the heat surfaces to attain reasonably high heat transfer coefficient and to prevent any local overheating. Viscosity of the fluid, which will often increase substantially as the concentration of dissolved materials increases. The tendency to foam, which makes separation of liquid and vapor difficult. Now we will see the single effect evaporator considered as a piece of process plant. The evaporator has two principal functions. The first one is to exchange heat and to separate the vapor that is formed from the liquid. For these two operations, it essentially consists of a heating source, that is here we are using steam as heating source, a vapor chamber, you can see here, and a condenser. Just we are going to recover the heat from the vapor. So these are the three principal components or sections of the evaporator. First one is the heat exchanger, which is having a heating source, usually steam. Second one is the vapor chamber. Then third one is the condenser, where the vapors are condensed. So the simplest evaporator is the single effect evaporator. The feed is fed into the heat exchanger. You have seen in the where the solution is heated beyond the boiling point of the solvent. The heat exchanger is typically a shell and tube heat exchanger, where the solution passes through the tubes and steam passes through the shell. Various types of heat exchanger tubes are here because we are telling that the heat exchanger is shell and tube, but with this shell and tube we are having various types like short tube, long tube, horizontal tube, vertical tube, and so on. All these variations are with respect to structure only, but the principle and design remains same. So here in the single effect evaporator, the vapors that enter the condenser need to be condensed. Okay, we will go from the first thing. The solvent evaporates in the heat exchanger. Okay, so the solvent is normally passed through the tube, whereas steam is passed through the shell. So it evaporates in heat exchanger. After evaporation, the vapor liquid mixture enters the vapor chamber, that is the next section, and gets separated. The vapor being light goes upwards and enters the condenser. The concentrated liquor leaves from the bottom of the vapor chamber. If the concentration is not adequate, a part of liquor is recycled and added to the field. In the case of evaporation, the condensate is not desired product. Hence, the vapors are directly mixed with the water since the vapors are usually water vapor. In this case, the condensation is very fast because of the direct contact of the vapors with the liquid. The barometric head to be properly maintained so that the condensate along with the cooling waters fall into the sump. In many cases, the liquid in the sump is cooled and recycled to the shower to dispense the liquid in the form of droplets in the condenser. If the condensate is the desired product and cannot be mixed with the solvent or water, we need to use the separate shell and tube heat exchanger in which vapors are condensed by indirect contact with the cold liquid. So maybe we can see the different types of evaporator. Based on the circulation, we are having natural circulation evaporators and forced circulation evaporator. The natural circulation evaporators consist of a tubular heat exchanger placed within a cylindrical vessel. The heat for vaporization is provided by the process steam which enters the tubes. These evaporators rely entirely on the free convection currents circulate the liquid to be concentrated. Horizontal tube evaporators are suitable for non-crystallizing solutions and low viscosity fluids. It can be done either batch-wise or continuous manner. So in horizontal tube evaporators, the tube bundle is called as calandria. It consists of a short tubes fixed to tube plates on either side of the evaporator vessel. The tube diameter is normally 25 millimeters and the evaporator diameter is between 1 to 3.5 meters. Vapor leaves through a de-entrainment device often consisting of series of baffles to prevent the carryover of droplets. In vertical tube evaporators, tubes between 1 and 2 meter long are held between horizontal tube plates in the lower part of the vessel. In this case, steam normally condenses on the outside of the tubes and the liquid to be concentrated rises in the tube, which are usually larger in diameter than those in horizontal evaporators. It may be between 35 and 75 millimeter. The circulation of liquids is aided by central downcomer. That is, the calandria is annular with the plan with the downcomer equal to between 40 and 100.